Great. So let's get started. So far we have been learning about how to really query your data that is organized in relational model, right? So just to refresh our memory, what is relational model? We think about our data and our knowledge as a collection of some set of tuples, right? So each relation contains a set of tuples. You can think about them as something similar to essentially a whole bunch of tables. Of course, there's a caveat because when you have a table drawn on a piece of paper, right, inherently you are defining some order for those tuples. In relational model, all of them are sets, right? All the columns are sets, all the rows are sets. There's no orders between different rows. There's no orders between different columns. And then we talk about what do we mean by query the data, right? Essentially, we talk about different query languages, relational algebra, relational calculus, whatever they are actually defining a function that take as input an instance of your database and output a new relation. So that's what a query is. So because there are different ways for you to write that query down, right? And we talk about these two different ways for you to get it done. There's relational algebra, where your view of your data is, okay, it's a set of tuples. If I treat them as a set, there's nothing stopping me from querying them with a whole bunch of set operations. So I can do that. Another alternative view of your data is, okay, it's not only a set of tuples, we can also see them as a collection of facts. Right? The moment we see them as a collection of facts of first-order interpretation, we are able to write a logical formula to query the information that we want. The difference between these two different ways of querying information is if you take the relational algebra view, you are actually telling the database, this is a step-by-step recipe that if you follow it, you are able to give you what I want. You are telling the database how to get it done. When you are writing a relational calculus query, you are not doing that. You are defining at a higher level what are the things that you really want. So one of these language is imperative, another is declarative. And we also talked about the relationships. So we start to lay down all of those query languages and arrange them in a way to see which one is more powerful, right? What does powerful mean? The power of a query language is the collection of functions that is able to be expressed using that query language. And we see clearly, right, relational calculus is more powerful than relational algebra. Why? Because you could have queries that you are able to express using relational calculus, but you are not able to express using relational algebra. And one such example is relational calculus. You could have something that is infinite as an answer, but for relational algebra, right, given a finite instance, your answer is always finite. And we also try to constrain the power of relational calculus a little bit because we don't want the user to have something that's infinite as an answer because that will never finish. We talk about different ways to constrain the power. We talk about one alternative semantics for relational calculus called domain-independent relational calculus. And we don't show, but I tell you, we didn't have the proof here, is this relational algebra and domain-independent relational calculus, they are equally powerful. Okay? Whatever you are able to write in relational algebra, you can write that in domain-independent relational calculus. And you can also constrain the power of relational calculus by not constraining the semantics, but also constrain the syntax. We talk about a subset of those query languages. For example, conjunctive query, that I only allow the user to write down a logical formula that only contains a conjunction of items. Okay? And also, there is the subset of relational algebra that doesn't contain all the operations, but only have 4 of those operations: selection, projection, drawing, and renaming. And we show they are actually equivalent in terms of how powerful they are. And of course, they are subset, so they are less powerful compared with relational algebra or domain-independent relational calculus. these are the 5 query languages we have been talking about. And then on Wednesday, we also switch gear and try to understand a little bit some query languages that is practical. Practical in the sense that that is something you are going to write down inside your database system. And that is something called SQL. And we talk about, as we will see, we are going to talk about different subsets of SQL. There are those queries that you can write by using select from where, which corresponding to conjunctive query and all the relational algebra with that 4 operators. And then we are going to talk about today some even larger subset that's going to allow you to write whatever query you can write in relational algebra or domain-independent relational calculus. And then, of course, we are going to talk about maybe, actually today we will also talk about it, something that you are not able to write, an even larger subset of SQL that allow you to write queries that goes beyond what you can write in relational algebra. So that's going to be the focus of today and also the focus of next week. So what is SQL, right? SQL is a family of standards to allow you to specify and manipulate data that's modeled in relational model. It has 3 different components, right? So first component is a data definition language. The goal is really try to say, I need to tell the system what my schema looks like, okay? So assuming you have relational schema look like this, you have relation named R with n different attributes. Each one of them have domain like D1 to Dn. In SQL, you need to specify the name of the relation, the set of columns, and the set of data types, right? Like most of the programming language, you have some predefined data type, right? And then to specify a schema, you could write something like this, right? You can say create a table with the name, followed by the list of attributes of that table. And for each attribute, you have the name and you have the data type. And then you'll say, the primary key here is the personnel number of the professor. And that gives you something essentially like this. The thing in the bottom is theoretically what it is, right? The thing above is actually the query you can actually write to a real-world database system to specify such a schema. And the second subset of SQL is data manipulation language, because once I define the schema, right, you can think about that. I have a whole bunch of tables with only the header, but there's no content. I need to put things in. I need to be able to manipulate the data there. Otherwise, I have nothing to query, right? So data manipulation language provides that functionality. So to populate the relation, right, you can do that tuple by tuple. We talk about this insert into statement, right? You insert into a table with a certain value, something like this. If you do this, you are going to actually populate these 3 tuples on the left-hand side. But this could be very slow. Why? Because every single time you have an insert into query, the system needs to parse the query and insert it and do some checking of the data type, all those type of things. That could be very slow. When you have millions or billions of tuples to put into this relation, right, that's probably not the best way to do it. So another way to do that in most of the database system is they all give you this bucket type of functionality that you can actually put your information into, for example, here a CSV file, right? Have a table somewhere, and you can say, just copy everything in this file, of course, given the format the database can understand, into this relation. So that's actually something most of the database systems today are able to support. And CSV is not, if you really have a lot of data, CSV is not really that efficient. I mean, it's more efficient than insert into, but it could be faster. You could just put your data into a binary form, and the system can actually load it much, much faster without parsing it, right? So if you look at these 2 things, right, now we know how to define a schema. We know how to put data into my relation. Whenever you are writing such a query, what are the things happening under the cover, right? Essentially, you have your database system, and then you have you as a user. On the other hand, you have your computer, right? You have your hard drive, and you have your DRAM. Whenever you are writing the create table statement, what's going to happen is a system, database system going to parse that query and going to create that table and store that on the hard drive. I mean, if you're talking about standard traditional relational database, that's what's going to happen. And whenever you are actually say, yeah, try to query it, right? So we are going to look at this later. What's going to happen is the database is going to bring the information all the way from hard drive to DRAM and then return the answer to you as a user. So this is the interaction model between you as a user and database as a system and your computer. The goal of the database system is to make sure everything happens on the left-hand side. You as a user don't need to worry about that. I mean, that's the goal. I mean, in practice, you do need to worry a little bit about that. But the goal of the system, in the ideal case, is to make sure you as a user write high-level declarative language and do not worry about how data is brought from the hard drive all the way to you as a user as an answer. Now let's talk about some of the ways to query information inside your database. Oh yeah, before that so before we talk about queries, so there's actually something interesting. Now we talk about these two different sub-family of queries you can write, like statement you can write, those kind of define the schema and those kind of put information into your table. So these two things can actually interact with each other. So let me show you one example. Let's see whether I can open it. Yeah. So this is actually something you can actually play with. So on the left-hand side, I'll try to see whether I can make this a little bit bigger. On the left-hand side, right, that's one query. Sorry, not a query, one SQL statement that create a relation, right? We can read that together, right? You create table R. That's the name of the relation, right? And here I have two attributes, A and B, right? And then I have my primary key, which is the column A. It's a relation with two columns, and I have a primary key. Once you run that, you actually will have such a database, such a relation inside your database. And then on the right-hand side, right? So I start to insert data into this relation. I first insert one tuple with a value 0 and 1, right? A equals 0, B equals to 1. And then I insert another one, 2 and 3, insert another one, 0 and 4. So on the left-hand side, that's a data definition language. On the right-hand side, that's a data manipulation language. If I run this SQL query on the right-hand side, what would happen? Right? So think about this. Well, these two subfamily of statements going to interact with each other. Because inside the data definition language, you are going to define some constraint. There's type constraint. I cannot put string into A, right? And there are key constraints. I cannot have an invalid instance. And in this case, it means that I cannot have two tuples with the same value of A, because A is a primary key. So whenever you are running things on the right-hand side, it is the job of a database to really check for you whether you are able to insert that tuple into the relation, whether that's going to violate some of your constraint or not. In this case, if you run these three different statements, right, what's going to happen is you are going to see something like this. So the first statement is fine. Okay, that's a green thing there, right? So first statement is fine. After I do that, I have a new relation with one more tuple. The second one is also fine, right? But the third one is actually going to throw an error here, simply because I already have a tuple 0, 1 inside my relation. If you want to insert another thing like 0, 4, it's going to violate your key constraint, because now you have two tuples with the same value in the column A. Okay? So there's certain interaction between these two subsets of languages. And then in PostgreSQL, this is the error message that you are going to see if you try to do the third statement on the right-hand side. Okay? Okay. So now we know how to define the schema, tell the database what your data looks like, and we know how to really put data into the relation. Now let's try to query it. The third subfamily of SQL standard is what we call a query language. And in this case, the really fundamental statement that you are going to write throughout the whole course and maybe throughout your whole career writing SQL queries is this statement, select from where. Okay? And it's actually very simple. So assuming I want to have some, do a selection query, right, to say I want to find all professors with a level equals to FP, right? So what are you going to do, right? As a human, what are you going to do? You are going to tell me, okay, I want to select all the professors, right? So what's that condition? Is level equals to FP, right? And that's pretty much what you have in the select from where statement. In this case, you select personnel number and the name of the professor from a relation, which is professor, where the level equals LP, right? That's almost human understandable, right? So this is actually the beauty of SQL because, yeah, everyone can read this and roughly you understand what you're trying to do. But this can be even more precise. Fundamentally, what this query is trying to do is try to specify a relational algebra query look like this. Okay? You have your relation, professor, in the middle, and then you do one sub-selection to only filter out those professors whose level equals to FP. And then you do a projection to only keep that two attributes, personnel number and name. Whenever you are writing that select from where query, what you are specifying to the database is something equivalent to that relational algebra query. Okay? Essentially, what's after from is the corresponding to this relation, and what is after where is the condition of your selection, and what is after select is your projection. That's the column or attribute that you hope to keep in your answer. Okay? So it's very simple. And sometimes, because we are talking about practical query language, of course, there are a lot of syntax sugar, right? So sometimes if you want to say, okay, I don't want to do projection, I want to keep all the attributes, okay? So essentially, in this case, we have 4 different attributes, right? So you are going to have projection, keep all of them. In this case, you don't need to write down all the attributes. You can just have something like star here, right? You can select star, meaning that I want to keep everything. Select star from professor where level equals P, something like this, okay? It's as simple as it is, right? So it's very simple. And you can do more with this construction. You can actually do join here. Assuming you say, okay, now I have 2 relations, I have professor, I have lecture. I want to know which professor is teaching database, right? In this case, what you can actually do is, I can actually join professor and lecture. And when I join them, my join condition is the personnel number of the professor is the same as the professor number in the lecture table. Okay? And I have another condition is I want the title of the lecture to be database. If you want to do that, the query you are able to write look like this. You select name, which is the projection that you take, from 2 relations, professor and lecture, where the condition is you want the personnel number of the tuple from professor is the same as the prof number from of the tuple from lecture. Another condition is you want the title of the lecture equals to database. Okay, make sense? And precisely, this gave you a relational algebra expression or something equivalent to that look like this. So essentially, whatever after from, okay, is a collection of relations that's actually semantically corresponding to this huge cross product. Whenever you put a lot of things in the from, essentially you're saying, okay, I want to consider the cross product of all the tuples in this relation. In this case, that's all the pairs of professor and lecture. And then whatever you put in where is the subselection. Okay? You can you can do, for example, natural join, right? That become essentially equality under the selection, right? You can do other things, right? So you can actually put essentially like after where is all the conditions that you use to filter tuples in that cross product. Okay? You can do theta join, you can do a whole bunch of things. And then of course everything after select is the projection. It's the tuple that you are going to keep. Okay, essentially from defines a little relation. You want to do cross product or you want to join. Where defines the selection condition, and the select give you the projection. And more generally, right? If you are writing a SQL query look like this, you select A1 as, you give another name for A1, you give like to AN, right? From R different, K different relations, R1 to RK, you have a whole bunch of conditions, P1 to PM. What's going to happen is this give you a relational algebra expression that looks like this. You take all the cross product for all the K relations, and then you apply all the sub-selection conditions, P1 and PM, which is after where. And then you do one projection, only keep A1 to AN. You do one renaming to give each attribute a different name. So fundamentally, whenever you are doing select from where, all you are doing is to specify a query that has an equivalent semantic as this relational algebra expression. Make sense? Any questions? Any questions? It's simple, right? Okay. Any question online? In this case, would it work with a join instead of a cross product? Yes, yes. Like you specify some type of conditions that are going to be equivalent to join, right? So, but logically, this is what you get. I mean, this is not what the system is going to run for you. This is semantically at logical level what you specify. Okay. Of course, system will not run the cross product for you, right? The system is going to say, yeah, it's actually a join. Let me run it as a join. Right? Okay. So, and you can do more, right? You can do more in SQL. You can take the union of two relations. I can take the union of the result of two queries, right? Because the result of query is also a relation, right? For example, you have the union keyword. You can actually use that to connect to select from where query or whatever query you have, right? So you can do this. You can do intersection, right? And then you can do difference. You write except. Something like this. Okay? You can also connect those queries together. And there are actually more. So let's look at this example and this query. On the left-hand side, I have 3 professors. And then my SQL query is very simple. I select level from professor. There's no where condition. So essentially, I don't filter anything out. Okay? So what would be the answer to this query? Let's think about this. How many tuple will we have in the answer of this query? Who thinks empty? 1 tuple? 2? 3? 4? Hopefully no one say 4. Okay, great. It's actually 3 tuples. Okay? So that's a fundamental thing. That is, whenever we are talking about a relational model, relation is a set, at least in this, at least in this course, at least in exam, okay? Relation is a set. Whenever you are interacting with a database system, relation is a bag of tuples. There could be duplicates, okay? You could have 2 tuples with the same value. So in this case, right? So on the left-hand side, you have 2 professors with level LP, 1 professor with level AP, right? So and then on the right-hand side, you are going to have duplicate tuples, 2 tuples with the same value FP. Okay, makes sense? That's why you have essentially 3 tuples on the right-hand side. Make sense? What if you want the set? You say, oh, yeah, I don't want the bag, right? So I really want the set. So additional keyword can do is something called distinct. Okay, you can select distinct level from a table, and this one will actually do the duplication for you. If you run this query, you are going to have something with only 2 tuples, like in the answer. Okay, makes sense? And then you can do more with distinct, right? You can do the duplication on a single attribute. You can also do the duplication on actually two attributes or multiple attributes. If you say, okay, I want to select distinct name and value from professor, how many output, so how many tuple would be in the output? Let's think about this. 0 tuple, 1, 2, 3, 4. Okay, it's 3 tuples, right? Because here, whenever you have distinct, it's going to deduplicate all the following attributes. In this case, if you have 2 attributes following distinct, it's going to try to say, okay, give me all the distinct tuples. Okay, not a specific value, but distinct tuples. It's going to check this pair. Okay, make sense? Okay, so again, the fundamental thing is distinct give you something that translates a bag, a multi-site, to a site. Okay, it's try to keep all the distinct tuples. Again, in most of the real-world database system, actually not like if not all of them, SQL implement a bag semantic. Okay, there could be duplicates as long as it doesn't violate the key constraint. Okay, so if you do not have a key constraint defined, it could have duplicates. It's not a site. When we talk about relational model, when we write relational algebra, when we do that, we always think about relation as essentially in this course, whenever we are doing theory, write things on a piece of paper, that's a site because it's easier for us to reason about it. Whenever we are talking about practical system, it's a multi-site. Okay. Okay. One statement that we can make is we have been looking at something very simple. We have select from where, we have union, we have difference, right? So we have intersection between relations. That's all we have been learning. But even this very simple subset of queries you can write in SQL is already pretty powerful. One statement that we can make is that every single relational algebra queries that we defined so far can already be written in the SQL subset that we have been looking at. So how to prove that? It's very simple, right? So what are the operations that we know in relational algebra? We have union, we have difference, we have selection, we have projection, we have cross product, we have renaming, right? That's all we need. In relational algebra, right? So you can actually have this type of things, right? So this is how you represent kind of the thing on the left-hand side. And we know how to write each of these in SQL at this moment. You know how to write union, right? You know how to write difference. You know how to write select, projection, cross product, and renaming. Okay? Whatever relational algebra query that you want to write, now we know how to write it in SQL. The consequence of that is every single first-order logic formula that you want to specify is also you'll know how to write that at this moment. Because if you take the domain-independent semantic of relational calculus, every single first-order logic formula in relational calculus is able to be represented as a relational algebra expression. That's what we learned from last lecture. And now we also know how to write down every single those relational algebra expression using SQL, right? Make sense? Question? Oh yes, for natural join, you just define in the where condition the natural join condition, right? So natural join is like if you share attributes, they should be equal. You just write it down, right? So that's one way to do it. There's also another keyword called inner join that actually directly gave you that. So once you can write, if you read the chapter 6 of textbook, you can write select from relation 1, join relation 2 on something. That's give you the natural join. Yeah, so that's a syntax sugar you can have. Yeah, so like this is a bare bone of what you can write in SQL. There are a lot of syntax sugar to allow you to something much easier. Okay, make sense? Any other questions? No? Okay, great. So this is the power of SQL, right? This is a relationship between these 3 different query languages: relational algebra, domain-independent relational calculus, and this very simple subset of SQL, which, as you can see, is very powerful. Every single first-order logic formula you can come up with, you are able to express that at this moment. And we are not even halfway done today. That's the power of database system, okay? So now we talk about this. In the bottom, there's select from where. And now we are going to look at an even larger subset, okay? We have select from where, we have the Sql subset corresponding to relational algebra, but as a practical system, you can do even more, okay? So essentially, there are other things you could do. Let's assume you have this relation professor, and then you can do sorting. By default, tuples in a relation doesn't have order. So when you do select from where from the single relation, you can expect all the possible orders, okay? I mean, in practice, it won't give you a lot of weird orders. Pretty much, sometimes it's kind of corresponding to the order you insert tuple into the relation, which makes sense, right? Like if you don't have index, like on the relation, it will give you something like that. But there's no guarantee. Whenever you do select from where, the system doesn't give you any guarantee on the order of those tuples, okay? Because the bag and set doesn't have orders. But in practice, maybe you want to say, yeah, I mean, I want to order those tuples, like, and show them in my answer, right? So one thing you could do is there's the order by keyword that you can have. You can put that after any select from where query that you have. Essentially, you have that query. You can actually order by tuples in this relation. So the way to do it, you specify the collection of attributes you want to do the sorting, okay? And if you put multiple attributes there, it's going to prioritize essentially the thing that you put earlier. If you have level and name, it will first sort the level, and then within level, it's going to sort the name, okay? So, and then you can say, yeah, I want the order to be descending, to be ascending, those type of things, right? So now let's look at this Sql query together. I select all those attributes from professor, order by level, I want that descending, name, descending, okay? What would the system give you? First of all, how many tuples is going to give you, right? 3 tuples, right? So I hope we agree on that. But what would be the order the system gave you, right? It gave you something that look like this, right? Here I put level first and name second, right? It means that whenever I'm ordering that pair, the partial order I'm defining is I will check whether, so essentially I will like sort the level first, and within the same level, I will sort the room. Sort the name, okay? All in the descending order, right? In this case, all the F is after A, right? So I mean, it's basically a very natural order if you do the descending thing, right? So it's going to put all the tuple with FP first and then AP, and then within FP you have a descending order on the name. Here you are sorting the string, which gives you a pretty natural way to define the order. Make sense? This is something that you are able to write. Again, tables are not sorted by default. If you put the relation in the table, it's not sorted at all. No matter what database show you, it's not sorted. Sometimes when you select tuple from that relation, you feel it's sorted in some way, but don't trust it. Yeah, so it's not sorted. There's no guarantee from the system about the order is going to return something for you. If you care about the specific order, you need to ask the database to order that for you. Okay? And there are more. You can group tuples together. You can do aggregation together, like of all those information. For example, I have this relation. I will say, okay, how many professors do we have, right? So far, it's very hard to answer that question because I don't know how to count things, right? So the way that database think about it is by model it as aggregation and group by. So another construction that we have in SQL is something look like this. Okay, you are select from where, right? All those things give you a table, and you can group by. You can group by a collection of attributes. So what's going to happen here is for every unique value of the attribute that you group by, here is a level. For every unique value of level, you are going to create a group. And for that group, there's a whole bunch of corresponding tuples with that value, right? You can think about this as partition, right? Group by level. I have two unique values for level, AP and FP. So I have two groups. I have the AP group, I have the FP group. For AP group, it's corresponding to the first tuple. For the LP group, it's corresponding to the second and third tuple. Okay, I have this. And then there's an aggregation function, the count star, which actually take as input a group and output a value. In this case, very natural. I want to take as a group, and I want to count how many examples are there, or tuples are there. Okay? In this case, it's going to give you two groups, because there are only two unique values for level in the relation. And for the first group, FP, I have two tuples. So count star going to, the aggregation function going to return 2, right, because there are two tuples. And the second group for AP, there's one tuple, so count star going to give you 1. Okay? If you run this query over that relation, this is what you are going to get. And you can use different aggregation functions. The signature of an aggregation function is a function that takes as input a collection of tuples and output a single value. Okay? So you can have sum, right? You can have average, you can have count, so on and so forth. As long as that fit that signature, right, you are able to run it. And you can actually define your own aggregation function if the database doesn't give you. But that's a signature. From a group of tuples, sorry, a set of tuples, and output a value. That's what aggregation function means. And then essentially semantics, right, is you first group the table by different values for the attributes in the group by. And then for each group, you apply the aggregation function. Okay? So let's look at this SQL query. Okay? What if I don't have group by? I only have the aggregation function. Right? So in this case, essentially the database is going to treat the whole table as a big group, because you don't specify how to group by, right? So I assume you want to treat the whole relation as a single group, and then I will run the aggregation function. In this case, if you want to select count star from professor, it's going to give you the number of tuples in this whole relation without grouping. Okay, makes sense? This is aggregation and also about grouping. So another thing that you could do is, once I have grouping, you can actually also filter the group. Okay? You have group by, then you have a whole bunch of groups. You say, yeah, I know for some of this group I don't like them. Okay? That's something you could do. You can actually have another keyword called halving, followed by group by. That's actually the last row here, right? To really specify some condition of keeping that group. And in this case, right, so for each of the group, you can say, yeah, inside this group, I do one aggregation. For example, I calculate the average, and I only keep those group with the average credit point, right, larger or equal than 3. And then what system is going to do is going to do the grouping, and for each group, calculate the average, and check whether the average larger than equal than 3. If it is, it's going to keep the group. Otherwise, it's going to essentially will not return that specific group. Okay, makes sense? And you can write kind of group by and aggregation in very complex queries. Right? In this case, I don't even know what this query is trying to do. Let's read that together. You join lecturer and professor. Okay, you say, and that gave you all the pair of lecturer and professor, and in which this professor teach a lecture, and then you filter all the professor with LP. And then from that table, you group by professor and name, and you say, I only want to keep the group where the average credit point that the professor is teaching is bigger or equal than 3, and then return the sum credit point. Right? So essentially, this one gave you all the professors whose level is LP, who teach on average 3 credit point, and I'm going to return you the total amount of credit point that professor is teaching. Right? This is what this table, like a SQL query, try to tell you. Make sense? Any questions? Questions? No? Okay. Question online? No? Okay. Great. So here, by having things, right? So you are filtering group. Okay. That's the difference between having and where. Where is try to filter the raw tuple before grouping. Having is filter out the group after grouping. Okay. So, and you can do more. You can have quantifiers there, right? For example, you can say, yeah, I want to select from professors where the professor is not in some result of some SQL query. You can also do this. You can have this kind of subquery type of thing, right? You have those uncorrelated subquery where you first run the thing in the you first run a subquery. You select a personnel number from lecture. That's all the professor who is teaching, right? And they'll say, okay, I want to have the professor who is not teaching. In this case, what do? You'll say, yeah, I want to find all the professors, but I want the professor personnel number is not in the result of this subquery. Okay? That's something you can do. So you can also do more correlated queries that become a little bit more complex. You can also do this. You can also say, I want all the professors, and here's my condition. My condition is, I want all the professors such that the subquery return empty. That's something you can do, right? So you can say, yeah, where not exist, you put a subquery. What's interesting here is this is a correlated subquery in the sense that if you look at this thing, right? So there's correlation between the main query and also the subquery, right? So what's going to happen here is logically, a system probably will not do that for you, but logically, what you are trying to specify in semantics is you try to evaluate the subquery for every single tuple in P. Okay, so that's a where condition. I assume I don't have this where condition. I run the query without this where condition. And then for every single tuple in that result, I run this subquery and I check whether it's satisfied or not. If it's satisfied, I will return, otherwise I will not. Okay? So logically, that's what's going to happen. It's not what's going to happen. Like logically, that's what you are specifying to the system. Okay? Any questions? So far, so good? Okay. So, and then, right, so I mean, logically, that's what's going to happen. Physically, when the system is trying to run that for you, what's often going to happen is the system going to automatically rewrite the query to turn that into something that's easier to run. So let's still keep, look at this one, right? So what's going to happen, the system, one thing could do is, essentially this one is actually corresponding to the join thing, right? So essentially, whenever you are writing this kind of correlated subquery, often the case, the system could transform them automatically for you such that it's easier for the system to understand. Okay. Oh, yeah, there's a typo somewhere, I think. There's some Slack professor from. Yeah, there's some question online. So which query are you talking about? Okay, so yeah, we can deal with that during break, I guess. Yeah. Okay, so another thing you can write in SQL is the whole bunch of keyword called any, all, and some. Okay, so that's another thing you can write in SQL. We are not going to cover that today. I want you to Google and learn it by yourself. Okay? And I promise you it will be in the exam, okay? Learn it. So that's the best way for you to learn SQL. I mean, if you don't Google it and read the PostgreSQL reference to learn about operators, that's very hard to learn SQL, okay? These three things will be in exam, okay? I promise you. So try to learn it. You Google it, okay? SQL, any, all, some, PostgreSQL, it gave you to that reference page, and read it. Okay? Try to think about, yeah, what does this three even mean? What's the semantic and how to use it, and play with it. Okay? It's very important for you to actually learn how to Google things when you want to write a SQL query, because you cannot remember all those keywords. Okay? This is very important. Okay? Do that when you go back home. Okay, so this is the first half of the lecture. Let's take a break, and when we get back, we continue SQL. Okay, so let's continue. Sorry. Okay, so everyone on Zoom can hear me, right? Someone give me a signal. Okay. Great. So we have been looking at a whole bunch of things you can do in SQL, right? Let's try to look at some examples. So look at this query. This is a database that we are so familiar with. Let's get all the students who take database, right? So in this case, we talk about two kind of theoretical way to write down that query, right? You can write down this query as a relational algebra expression, right? You have student join, natural join attendance, natural join lecture. You select the title of the lecture by database, and you project on the student personnel number. Equivalently, you can write a relational calculus query look like this, right? So this is actually a logical formula like look like this, right? So I mean, yeah, so it's very natural to parse it. In practice, what you are going to do in a database system, right? You can actually write this down as something like this, right? You select you select your information from 3 different places: the students, the attendance, the lecture, right? So that gives you a huge kind of cross product. And logically, physically, it's going to the database is smarter than that. Your condition is, okay, I need to specify the join condition for the student and the lecture. That's a natural join. I know about that. So the students, the personnel number in the student relation need to be equal to the personnel number of the attendance relation. That's define the natural join between student and attendance, right? You can also write that as student join A on personnel number. I mean, that's also something you can do. And then the second condition is you want to say, yeah, the lecture ID on A need to be equal to the lecture ID in L, because then that's a natural join between attendance and lecture. And then you filter all the tuples by L.title, the title attribute of lecture of the lecture relation equals to database. And then you do a projection, only keeping the personnel number of the student relation. They pretty much give you that relational algebra expression, right? And that's actually something you can do in database. So far, so good, right? Okay. And you can do more. Let's find the professor who don't teach, right, in this database. What you are going to do is, okay, if you write that as a relational algebra expression, you need to do that in 2 steps, right? You need to say, okay, let's get all the professors. And you could do that by just do a projection of the personnel number in the professor table. That's all the professor. And then you do a difference, right? You minus all the professors who teach. That gives you the professor who do not teach. So in this case, you can actually join the natural join. Actually, not natural join because they don't share attributes. So the professor relation with the lecture relation, you matching the personnel number in the professor relation with the prof number in the lecture relation, right? And then you do a projection to keep all the professor. That give you all the professor who teach. You do a difference that give you the professor who do not teach. If you write that as relational calculus, right, it's going to give you like this, right? So essentially, that you have 2 conditions. That tuple need to be a professor, and also there doesn't exist any lecture that a professor teach, right? If you write that in SQL, you could have something like this, right? You could say, yeah, let's select personnel number from professor. That give you all the professor who teaches. Sorry, like all the professors in the system. And then have a second query. You select the personnel number from the professor from the 2 pieces of information, professor and lecturer. You join them together, right, with that where condition, and you do the difference between these 2 queries. It's simple, right? And you can do more. We are not going to go through all of this, right? But we will go home, right? So try to look at this example, and this should be pretty easy to understand, okay? So now let's see a database in action about how to really interact with that. In next week, okay, I think Friday or the Wednesday in the week after, we are going to have 2 hands-on sessions. You bring a laptop here, and we are going to write SQL together. So you are going to see more about the interaction next week. But one thing that we provide is you need to install your database somewhere, okay? So there are multiple things you can do. if you do not want to install your database, so we have a catacoda somewhere. Okay, so if you go to here, that's require you to log into something. We have essentially, and this one going to give you a virtual machine inside the browser. You don't need to install any like it already gave you a Linux kind of terminal. What you can do is you can actually follow this one by one. Then you can actually install a database, right? So we actually write it down pretty clearly, right? How to install a database inside Ubuntu, right? And how to connect to a database, right? And also how to list the databases, all the type of things, how to query it, right? Just give you a very simple example about how to install a database, how to query things in a database. It's in the same environment to make sure you don't have all those kind of dependency problems, right? So if you want to log into Catacoda, this is what you can do. You can, of course, you can also install a database all by yourself on your local machine. The same tutorial in Catacoda is actually on GitHub, right? So there's a whole bunch of files, step 1 to step 5. You follow them one by one on a reasonable Linux machine. That should give you the same thing, okay? So what I recommend is you go home. Either you do the Catacoda thing if you want to log into that, or you follow the GitHub thing and install that on your local machine, and go through the tutorial by yourself. Okay, it's very important for you to know how to install database and actually write the SQL query. It's very different. Yeah, it's a different feeling when you see that on like on a piece of paper on slides, compared with you actually writing it. Okay, I mean, I hope I can teach you that like during lecture, but there's no way I can do that. Okay, open your laptop, right? Do either of this, install database, and follow this kind of very small tutorial and play with database by yourself. Okay. Next week we are going to have 2 lectures. Just we write SQL query together. Okay. But it's very important for you to install database before that to make sure we have something to work with. Okay. If you do not want to install, you can always do the Catacoda things in the browser. Yeah. Okay, so this is a lot of things you can do in SQL. Now let's talk about some additional things. If you look at the query language that we have been introducing so far, there's always one fundamental assumption that we have so far that we want to break at this moment. So far, we always assume essentially, you know all the information. Well, what do I mean, right? So I'm going to put these 2 tuples in the lecture table. In future, I'm going to say, yeah, I know there is 2 lectures, and I know all the information about them, right? There are nothing that I don't know about this. And we give you the ways to actually extract insight and facts from the things that you know. But we never give you a construction to allow you to say, I actually do not know about something, right? And that's very important, because knowing something is very important, but knowing that you do not know about something give you actually a lot of more, not a lot of more, but also a lot of information, right? So how can we model the things that we do not know? And that is something we are going to talk about now. So in practice, when you have a database, either during query processing or either during the data collection process, when you put data into the database, you could have incomplete information, right? And incomplete information come from everywhere, right? There could be, for example, you have a lecture, you don't know which professor is teaching it at this moment, then you don't know about that piece of information. So what should you do, right? We need some construction to allow us to tell the database, these are the things that I do not know. These are the information that I do not have yet. So that is the goal of what we are going to talk about at this moment. So there could be a whole bunch of reasons. Some of this information may be not applicable, right? And maybe some of these things are simply like missing data, right? And so on and so forth. How can we model incomplete information? And also, how can we query it? And that's the 2 fundamental questions we really want to understand. So today we are going to really scratch the surface because it's a really deep question. If you look at these 2 questions, right, it's very fundamental and deep. We can have the whole course about how to deal with incomplete information, because there are so many different ways you can actually express incompleteness. Sometimes you have a prior to say, yeah, I know this one is more have higher probability than that one. You can also specify it in some of the database today. So we are not going to do that. We are going to take a very simple view of what do we mean by incomplete and what do we mean by query incomplete information. Okay? So the way that we are going to do that is by introduce a special state you can put into your database called null. Okay? So it looks very simple. Assume you have this lecture table, say, yeah, there's some lecture I don't know which professor is teaching it. You just put this special state null there. And that looks like a value, but it's actually not a value, it's a state. Okay? It's the state to say, yeah, I actually don't know about that thing. I don't know about that, the value of that cell. That's a state, that's not a value. It's going to be very clear what I mean by state. Yeah. So this is, yeah, that's it. Yeah, if you don't know something, there's a special state for you to put in called null. Yeah, that's as simple as that. Okay? Whatever you don't know, you put null. Okay? So if you remember last lecture, we talked about, yeah, if you don't know something, you can leave that as empty, right? So still remember that. This is what we mean by leaving that empty. Okay? Whatever you want to keep empty, you say, yeah, I don't know about that value, you put null there. Okay? It's a special state for the cell. Okay? So there are other ways to encode incomplete information, but null is the most popular one that is used, at least in practice. Okay? In theory, there are a whole bunch of things you can do. So what do we mean by null? Right? By putting that as state. What is the formal semantic of that? And also, what do we mean by query a relation with null? So there are different ways to teach this. So let's go from the more formal way of understanding what that thing really is, and then we try to define the practical way. So again, I mean, even for now, there's a whole bunch of things you can do. If you go to Alice's book, there's a whole chapter about incomplete information, and we are going to scratch the surface, really scratch the surface. So null is a state, it's not a value. And what do we mean by, for example, you have this relation, right? You have 3 people here. Yeah, for Kevin, we don't know the age. And you query it. You say, select all the person from this relation where the condition is age is smaller than 30. What would be the answer? Right? And what do you want the system to give you as the answer? So it's a very deep question. There's so many different you can define it. But fundamental principle, at least in most of the practical database system is trying to do, is to try to think about incomplete information as something that, as a state that you could put everything there. So that is how database think about incomplete information is. Okay, you don't know what that value is, so I will assume you could put all the possible value for age in that cell. I could have a whole bunch of possible worlds that do not have this null. Your table could be with age equals to 1, with year age equals to 2, equals to 30, so on and so forth. Right? This is how database think about incomplete information is. If you don't know that, what I assume is everything could be there. Okay? You have all those possible worlds. And I know how to answer query for each of those, right? Because there's no unknown for those possible worlds. For each of these, for example, if I evaluate the same query in the first possible world where the age equals to 1, I'm going to have Kevin in the output, right? Because 1 is smaller than 30. For the second one, yeah, I have Kevin there. For the third one, I don't have Kevin there because the value of age could be 30. When that happens, Kevin's not there. I do this over potentially infinite amount of those things because I have infinite domain. How to return the answer to the user if I think about incomplete information in this way? So many different things you could do to aggregate those information over this infinite amount of possible world. But one way, probably the most natural way, or at least the simplest way, is to return the thing that you are sure about. To return the tuple that you are sure, no matter what value you put in to the null state, that tuple is going to be there. In this case, it's a tuple corresponding to Anna, right? I don't care what value you put into your null state. in all the possible world, that tuple is going to be there, so I will return that to you as the answer. Okay? This is a very specific way to model about incomplete information and model about the semantics of how to query about incomplete information. So essentially, in this semantic, the database tries to be as conservative as it can be to make sure whatever I give you, I'm really sure about. It has nothing to do with what you do not know. It doesn't matter all those information that you put into the null state. This answer is going to be there across all the possible ways. You can instantiate in that unknown state. Make sense? This is beautiful, right? This is a principled way for you to model what do you mean by I don't know, right? This is extremely beautiful as a piece of theory. And also, this is logically what's going to happen, okay? Logically, this is what incomplete information is. But of course, in practice, when you are writing a SQL query to your database, of course, not going to do this, right? There's infinite amount of those, right? So there's no way I can go through all of them and aggregate them back and give you the answer. In practice, how people implement this very beautiful semantic is by defining some special arithmetic to manipulate the null state. So what people do is to say, okay, if you want to manipulate the null state, if I say, yeah, I have some value, some state is null, in the query, I need to say null plus 1. That special arithmetic going to give you also null. Okay? If you whatever you do over null is going to give you null. And when you compare the null value with some other value, it's going to evaluate not only to true or false, it's also going to evaluate to a value called unknown. Whenever you are trying to say whether this null value is equal to that null value, system will not say true or false. System will say unknown, I don't know. It's evaluated to essentially like a 3-value logic system, contain not only true or false, but also unknown. And then if you say, yeah, whether this null value is smaller than 13, I don't know. Right? You can put whatever there. You could put 1 there, could put 20 there. I don't know what the answer would be. Right? This is a very easy way to implement that all the possible world thing, right? Because, yeah, so I now have more information about what you want to do. I do not need to enumerate all of them. Yeah, I know if I have null there, I could put all the possible values. I could something smaller than 13, I could something bigger than 13, right? At the end of the day, I don't know what it is, right? I don't know what the answer would be. You want to check whether 2 null, one is larger than the other one? I don't know, right? I mean, the first one could be larger, the second one could be larger, I don't know. I will just tell you I don't know, okay? And then that gives you a 3-value logic system that look very, very natural, right? If you take the not of true is false, not false is true. If you take the not of unknown, it's still unknown. You don't know what that thing is, right? You can have this and, you can have or, right? To define this very natural 3-value logic system over this. And that gives you something that you can work with, okay? So now let's look at this example. You have a lecture relation with one lecturer, you don't know which professor is teaching that. Assuming we run this query, what would be the answer? I select everything from lecture with the following 2 conditions. Is either professor number larger than 2,200, or this professor number is smaller or equal to 2,200. So let's think about this. Let's think about this query. How many tuples do you think will be in the result? Think 0, 1, 2, 3. This one is going to give you, essentially, the way to think about it is you look at these 2 conditions and think about what the first tuple is going to give you. The first condition is going to give you unknown, right? Because you are comparing null with 2,200. I don't know which one is bigger. The second one is going to give you unknown. Yeah, because I don't know whether it's smaller or equal to. You put 2 unknown together, you have or. You look at the truth table, you get unknown, right? I don't know. Unknown or unknown, I don't know. Yeah, I have no idea what that is, right? So it could be true, it could be false, it could be unknown. I don't know. In this case, the where condition only returns tuples that evaluate to true. Okay, so that's the thing. So it's not going to give you unknown, not going to give you false. So that's semantic of where. So in this case, it will only give you the second tuple and the third tuple without the first tuple, because the first tuple, the condition is going to evaluate to unknown, which I'm not going to give you. Okay, so you can see the connection between this very simple way of dealing with null and that very beautiful logical semantic about incomplete information, right? So why are we able to do this? The reason we are able to do this is we have more information about what we are doing over that null value. I'm comparing it with other people, I'm doing other things, right? So because of that additional information, you are able to implement that really beautiful principal semantic in such a simple way. And that's interesting. And you could do more complex queries, and at the end of the day, you might need to enumerate all the possible values to have the principal semantics, right? And sometimes people do that, right? It's not often the case you can actually implement this semantic in this way. But for the SQL query we are looking at, yeah, this is what you need to do inside database. Any questions about this? No? Any question online? Okay, this is a very interesting question. Let me show this to the. Okay, so this is a question. So if we have a variable character field, you can see about that string, how is the following thing going to evaluate? Null equals to the string null. What do you guys think? Who think this one is going to evaluate to true, false, unknown? It's unknown. Yeah, for whoever asking that online, it's unknown, right? Because the way to think about it is I could instantiate that null thing and the first null, okay? As whatever string you could have. It could be equal to the right-hand side. It could be an empty string, right? Sometimes give you essentially true, sometimes give you false, right? Depending on what you are instantiating that with. And essentially in this case, whenever you are comparing a thing with null, I think in most, if not all the cases, there could be some counter cases I don't know about, but in most of the cases I can think about, whenever you are comparing with null, you have null, okay? That's a very good question. Okay, now let's look at some more interesting stuff. So now essentially introduce many corner cases in SQL. That's probably the only thing you do not want to see during exam because most of the corner cases will come from null, actually. Yeah. So again, like this query, we have a pretty good handle on, right? So yeah, you have this. Now let's look at this query. How many tuples will that give you? All right, just like start from lecture, right? So this one also give you what, like 3, right? Because there's no condition for filtering my tuples, right? So if you select start from lecture, I'm going to give you everything in that table. So operations over null, right? Null is a state, not a value, right? If you want to compare two null value, it's going to give you unknown. But what if you want to check whether a cell is null or not? I cannot compare, right? Whenever I compare, you tell me I don't like you don't know. So what if I want to say, yeah, give me all the tuples that that attribute is in a state of null, right? In this case, there's a special thing you can do. It's called is, right? So that's a special comparison operator you can do. If you say null is give you true, okay? So we can actually look at this more concretely. You have this lecture table. Assuming you write this query, you say, yeah, select from lecture where personnel number equals to null. This one gave you pretty much, Nothing, right? Because personnel number equals null will always give you unknown. You could put a whole bunch of things into null, but some of them are true, some of them are false, I don't know. What if you want to say, okay, I really want to have the first tuple? What should you do? You could write a query look like this. Select from lecture where the personnel number is null. Is about checking the state, not comparing a value. That's why it's important that null is a state, not a value. Okay? I can check whether that cell in your table is in that state or not. And the way to do that is by having okay, yeah. The way to do that is by having the is comparison operator, right? If you do this, it's going to give you something like that. It's going to give you the first tuple. Because the personnel number, personnel cell of the tuple is in a state of null. Okay? So that's how to actually compare whether some value is in that state or not. It's getting more interesting. We will try to think about aggregation. Okay? So let's go through multiple corner cases here. So assume you have this table. You have employee ID, you have name, you have department, you have salary. The whole bunch of null information there. The null information in department. There's null state in like salary. Whenever you have group by, okay, aggregation, all the null value go into form a single group. Okay? There's no reason behind it. It's just what the system decide to do. Okay? So now you could have alternative semantics, to be honest, right? But in database, at least most of them today, if not all of them today, it's going to treat all the null value as a single group to say this is a group that I have no idea what the value is. Okay? So for example, if you run this query, you select department from employee, group by department. What's going to do, right, is actually try to give you these three different groups. One is IT, another is finances, the second and the third one is actually null. All the tuple with the null value in the group by attributes going to become a single group. Okay? What if you have null in the tuple, in the aggregate tuple, not only the group, right? So in most of the cases, they will actually ignore the null value. So let's look at this example. I want to select from department, from employee table. I group by department. My aggregation function is I want to calculate the max salary of that group. So in this case, if you look at, for example, the IT department in the last row, right? You'll say, yeah, the salary is null. In that group, when I do the aggregation, I have some concrete values. For example, I have John Smith's salary is 2,000. Yeah, in that group, great. I have another tuple where the salary is null. You are asking me to do a max over this. What should I give you? In this case, most of the operators, actually not all of them, will ignore the null value. So in this case, if you do this, it's going to return these three different tuples. For the IT group, it's going to take the max between 2,000, 1,000, and null. It's going to just ignore the null value and give you 2,000. Make sense? And for the null group, it's going to do the max between 2,500 and null, right? It's going to give you 2,500, going to simply ignore the null value. And there are cases that will not ignore null. For example, if you have count star, okay, as an aggregation function. So what would this give you? I want to select from employee table, group by department, and for each group, I want to count star. So the semantic of star is a little bit special. It is the existence of the tuple itself, okay? So in this case, it's going to give you actually 2 for the null group because there are 2 tuples. right? So for the IT, you can use three group, so three, because it has three tuples in that group. And if you do count salary, not count star, it will ignore the null value for you. Okay? So essentially, if you do this query without, instead of doing count star, you do count salary. Okay, you have a specific thing there. It will give you essentially something like this, right? For the IT group, it only give you 2, not 3, because there's 1 that's null. I will just ignore it, right? For the null group, it's going to give you 1 tuple. It's going to ignore the tuple with null value. So far, so good, right? Now, all those corner cases will have null inside aggregation, but it pretty much makes sense, right? Okay. And there are more. So assuming there are null in the value, when there are nothing to ignore, what would you get? Assuming I have a group. Yeah, so look at this example. All the salary are null. For some reason, I know nothing about salary in this table. And I give you this query, max salary, what would I have? In this case, for all those groups, all I have is a whole bunch of null value. I do the aggregation, right? We just learned that you are going to ignore all the null. Then I ignore everything. And then I want you to take the max. What do you have? Yeah, you have null in the output, right? But there's nothing to ignore. You force me to aggregate. I will tell you, actually, I don't know what you mean. Just give you null. Okay? Make sense? When there's value, when there's null in the value, we want to aggregate. When you need to ignore the null, and when you ignore everything, you have null in the answer of that aggregation operator. Make sense? I don't think we have more corner cases. Yeah, that's it. Any questions about how to manipulate and how to query a database with null? Incomplete information? No questions? And one question online. Okay, this is actually a very good question. Wouldn't it make sense that max salary yield unknown if there is null value in the IT group instead of taking the max of the known value? Yes, you could define this alternative semantic. It's simply not what happened in the SQL standard, right? So you could define what you mean by aggregating over unknown in so many different ways, okay? And in theory, people do. For different ways you treat what you mean by aggregating over unknown, there are different things. But in practice, what people settle down in relational database, at least in SQL standard, is to ignore the null when you do aggregation. I guess, I don't know why, right? I guess essentially in practice, it'd probably be very frustrating to the user when the aggregation return null when there's just one unknown value out of a couple million of possible values, right? So that's probably the reason, I don't know. Yeah. Okay, so any other questions about information processing or unknown? Okay. Now the second question that we want to understand is, okay, so where does unknown come from? Where does null come from? So there are multiple ways you can have a database with null information, or you can populate your database with null. So first thing is something that we saw in the last lecture. That is, if you have an insert into query, for example, you have essentially three, one relation with 3 different attributes. When you insert something, you only give me 2 attributes. What should I do with the other one, right? Last lecture, we talked about, yeah, you keep them empty. What do we mean by that, right? So what do we mean by that is actually you put the null there into the attribute that's not specified in the insert into relation. Okay, that's something could happen. So another thing that you could do to introduce a null value into your system is that we can actually extend our relational algebra operations to introduce some additional operators that are going to give you a null value. So this is one additional operator that you could do. It's called a left outer join. So what it's going to do is, okay, I want to join these 2 relations on the C attributes. In natural join, right, what are you going to have? You only keep, assuming you are doing natural join between these 2 relations, right? You will have 1 tuple in the output. because the C1 is only thing that matches. In left outer join, I'm going to keep all the tuples on the left-hand side, because the left outer join, that's what we mean. We keep all the tuples on the left-hand side. If I am able to find a matching tuple from the right-hand side, I will put it in. If I cannot find it, I will fill the value with null. Okay? This is left outer join. In this case, you are going to have something that looks like this. It's going to, for C1, I'm able to find the corresponding tuple on the right-hand side. So I have a tuple with 5 values. All of them are concrete values that I know. For C2, I cannot find anything on the right-hand side. So what I will do is I will keep the D and E as null, because I don't know. Okay? So this is one operator in relational algebra that you can actually introduce those null values called left outer join. And of course, there's nothing magic about left, right? So there's also right outer join. You can actually keep all the information on the right-hand side. And if you cannot find the corresponding tuple from the left-hand side, you are going to put the null value into your result. Okay, make sense? And of course, you can do outer join. You can keep both. Okay, so if you do outer join, you are going to actually keep all the tuple from the left, all the tuple from the right. If there's matches, great. Then they appear in the same row. Otherwise, I put null. Okay. For example, for the second tuple for C2, it appears on the left-hand side, but I cannot find the corresponding tuple from the right-hand side. So what I'm going to have is ABC is a concrete value and D and D is null, because I cannot find that on the right-hand side. For the value C3, I'm able to find that on the right-hand side, but there's no corresponding tuple from the left-hand side. So what I'm going to do is to keep the left-hand side as null, because I don't know. Okay? So it's very, very simple. 3 operators that you could use to actually introduce null value. You can also write that in Sql, right? So in Sql, there's a kind of keyword called left outer join. If you want to do left outer join between table 1 and table 2, you just like select from table 1, left outer join table 2 on something. Okay? So that's something that you could write in SQL today. And if you want to do left outer join, if you want to do the full outer join, you do the full outer join. Okay? That keep both sides. So this is about information processing, essentially over incomplete information. The theory is very beautiful, but the practice is actually really simple. Okay? Okay, so before we move on to more SQL queries, any questions so far? What we talk about? Yeah. Yeah, then you're going to have multiple of those. So whenever you are going to find a match, it's the same as what you would get in natural join. Four. Yeah, that's why defining join using cross product is very clear, right? What is join? You do cross product, you filter. Okay? In that case, you have 4. You filter nothing else, done. 4, right? Okay. Any other questions? Other questions? Question online? No? Okay, now let's talk more about SQL queries, because I have more. So let's talk about one, and not corner case, but something you need to know. When you try to do statements in the data manipulation language, is you are trying to say, yeah, now I want to update my data. So there's a whole bunch of things you can do. You can insert tuple, you can update tuple. We saw a whole bunch of examples in the last lecture, right? You can do a whole bunch of things. What is the semantics when you do the updates? If you look at all these 4 queries, this question doesn't really matter too much, right? Who cares about semantics? I mean, the semantics is clear, right? I insert tuple into this, so I have the old relation. I define a transformation of that relation into a new one with one more tuple, right? So it's very natural. you delete students with semester larger than 13. Yeah, I have an old relation with a whole bunch of students. I transform that into a new relation in which I do not have those tuple with semester number larger than 13, right? So semantics is very clear. I set student set semester equal to semester plus 1. Yeah, what do? I define a transformation. I have old table, I have a new table. The new table, the only difference between the new table and the old table is all the semester number in the new table equals to the old semester number plus 1. So yeah, you don't really need to go through the process of defining a formal semantic for this. I mean, you could, but I don't see what benefit you can get out of it. But the reason we care about the formal semantics here is you could have some very interesting query. So assuming you have a relation look like this. This is the requires relation to say, yeah, on the left-hand side, sorry, like in the first column, it is the prerequisite. There's a course you need to take for the follow-up course. This is this relation. You could also write in the update query that look like this. And then you really need to define what do we mean by updates and delete from. So here, I want to delete from this relation where prerequisite is in the result of another SQL query. Okay? So another SQL query, unfortunately, also use information of the same relation. Make sense? I could do this. You say, well, if you look at what I'm trying to do here, in that SQL query, I'm finding you all the lectures that requires a prerequisite, right? Essentially, if you think about this requires relation as a graph or as a tree, right? You start from a couple lectures. It's not a tree, it's a forest, right? So it's not forest. It's a DAG. Okay. So you start from a whole bunch of lectures that doesn't have prerequisite. When you come into ETH, you can take it, right? And those courses must exist, right? So otherwise, like how can start, right? You have those courses without prerequisite, and then you have the thing you take once you clear up those prerequisite. The subquery give you essentially all the non-root node. That's all the courses that with a prerequisite. And then I want to remove all the tuples in the requires relation that prerequisite is in that set. Okay, so this is what intuitively what we are trying to do. When I run this query, because there's the nested kind of structure here, what do I even mean by this, right? So what system is going to do is to think about this in two different phases. It's going to run the inner query and try to mark all the tuples which are affected by this update query. But it will not update it. It just mark it to say these are the tuples that I'm going to do something about. And then in the second phase, is implement all the updates of the market tuple in a single run. Okay? So in this case, what we are going to have is in the first phase, you say, okay, this tuple, the prerequisite, right? So 5041, right, is in the result of the subquery because the first row corresponds to that. And then the second, and this tuple is the same, this tuple is the same, this tuple is the same. You say, yeah, in the first pass, I do not update anything. I will just mark it down. So say, these are tuple I'm going to delete, but I don't delete them. Okay? These are tuple I'm going to delete. And then the second pass, you implement all those updates by deleting them. Okay? This is how database think about this nested query, is to decouple them in a way that you first compute your updates and then implement your updates. Okay? So the thing about why the system really need to do this is the moment you mix these two phases together, you are going to have non-deterministic result. Okay? So this is just one example. Assuming you have this table, the same query, you have like B relation A, C relation B, D relation C is a chain. Okay? Assuming I mix them together, I say, yeah, the moment I know which one I should delete, I delete them. You could say, okay, you delete the second one, because the second one should be deleted. But the moment you do that, you are not going to delete the first and third one, because now they are fun. The moment you kind of mix it together, you start to have a whole bunch of ways you can update your table. And the second way is you just mark it down, you delete them, then you get this. You can now mix these two together. The moment you mix it together, you have non-dependent result, which is not something we really want for the user. In a database system, the first one is wrong, okay? That's not what the database is going to give you. The second one is what you should expect from the database, okay? So that's all for today. Next week, I'll see you guys on Wednesday, and we continue to talk about SQL.